Chapter 1, Section 4, on continuity and one-sided limits. Now, actually, we have talked in a sense about both of these topics. We talked about continuous as far as like what a well-behaved function is, continuous function in the last section, and we've talked about one-sided limits, not by their purest definition, but by looking at a limit from the left side or from the right side. We're going to go a little bit deeper into those. A well-behaved function is one that has no breaks or no corners, but mostly we are worried about there are no breaks. There are no holes in the graph, there are no gaps, there are no vertical asymptotes. When this happens, we say the function is continuous. Now, with that in mind, I want to look at these three possibilities as far as what can happen with a function at a particular value. The function is y equals f of x. Here, I'll write that down. Y equals f of x. And we say that f of c is not defined here. So you would see, hey, there's a hole in the graph. This is not continuous at x equals c because there's a hole there. Whereas in this example, the function f of c is defined. It's up here, whatever this value is over to the left. I don't know what that would be because I didn't set up the scale that way, but f of c is defined. However, the limit as x approaches c of f of x doesn't exist, because as we mentioned before, as we look at it from one side and we look at it from another side, there are two different values and the limit has to be unique. So the limit doesn't exist. Now look at this and you can see there's a gap right here, so that clearly would look like there's no continuity at c. Now in this example, f of c is defined, the limit exists, and the limit is whatever this value is up here at this line right there. But notice that the limit of the function does not equal f of c, which means we couldn't find this limit by using direct substitution. So we can somehow cure all three of those things. And again, there's a gap, there's a hole there. We can talk about what it means to be continuous at a point. So here's our definition. Continuity at a point. A function f is continuous at c if the following three conditions are met. That f of c has to be defined, right? That's what we were talking about, wasn't happening here. That the limit as x approaches c of f of x has to exist, which didn't happen here. And that the limit as x approaches c of f of x has to equal f of c, which is what didn't happen over here. So we can fix these three things, then we have continuity at that point. And it really comes down to the third one. Okay, because if f of c is defined, you can see there that f of c would have to be defined, and you could see that the limit would have to exist if it equals something. So it kind of comes down to the third piece of criteria, but we typically will look at it from stage 1, stage 2 to stage 3 when we're looking at whether or not we have continuity at a point. Now, most functions are defined for infinitely many points. The domain is infinite. But since we can only look at continuity at a point, one at a time, it would be impossible to be able to check to see if a function was continuous on its entire domain. So what we have here is a definition that allows us just a little bit of luxury on this particular idea, in that we don't have to prove it at every single point. Continuity on an open interval, not closed interval, an open interval. A function is continuous on an open interval, a, b, if it's continuous at each point of the interval. Now you say, well, gee, thanks. How do I prove that it's continuous at each point of the interval? Well, that's a common. We're going to be getting a few more theorems to help us with that. A function that is continuous for all real numbers is stated to be everywhere continuous. I kind of like it with the word everywhere before the word continuous. Sometimes I say continuous everywhere, but everywhere continuous just sounds cool. All right. Now, if f is not continuous at an x value, let's say c, then we say f has a discontinuity at c. All right, and there are two types of discontinuity. There are removable discontinuity and non-removable discontinuity. Hang on a second, let me grab a sip of coffee. All right, back at it. Now, removable discontinuity and non-removable discontinuity, I can kind of get back to here, to these diagrams. If it's just a hole in the graph, like it is here and like it is here, these are removable discontinuity, because all you'd have to do is redefine what c is. If we put c, f of c, not here, but up here, kind of just fill the hole, great. We've remove that discontinuity. Same thing here, we'd have to define a single point f of c to be right at this value, whatever it might be, and we remove that. We've kind of plugged the hole, so to say. But here, there's a gap. And because there's a gap, like if we had a vertical asymptote, for example, because there's a gap, we can't remove that. We can't twist this thing around to connect the ends, because we'd have to redefine the values for an infinite number of x values of our function. So we cannot remove that, but we can remove them if it's just filling like the hole. Okay? Now, let's discuss the continuity of each function. Now, this is not as bad as it sounds. It sounds a little weird, but this is not as bad as it sounds. Okay, f of x is equal to 1 over x minus 2. We know from algebra that we have a vertical asymptote at x equal 2. So it's not continuous at 2, but it's going to be continuous everywhere else, because no matter what we plug in, we're going to get a value and we're going to have a nice smooth curve. You may remember that for a function like this, we would have, if you can see this very well, I'm not drawing very dark, let's say 1, 2, if we have something like this where we have our vertical asymptote, our graph is going to probably look a little bit like this. Notice how it's smooth with no breaks, no holes, no gaps, except, of course, at x equal, well, I didn't get that very close here, but at x equal 2, I'm going to bring that a little bit closer there. There we go. So this is continuous everywhere except at 2. So what we're going to say is continuous from negative infinity to 2, and then union from 2 to infinity. Because it says to discuss its continuity. Now, when we discuss continuity, we find where it's discontinuous, and then we keep everything else. Now here, and by the way, this would be non-removable discontinuity, because we certainly have a gap here. This is going to negative infinity, this is going to positive infinity. Now over here, we also know that x cannot equal 2 here. But we don't have a vertical asymptote. We have a hole in the graph at x equal 2. Because we know that x squared minus 4 is x minus 2 times x plus 2. And that these would cancel. So you would have y equals x plus 2, which is the equation of a line, except x can't be 2. So at the point 2, 4, because I would get 4 if I plug 2 in here for x, at the point 2, 4, we have a hole in the graph. So same thing here. This thing is continuous from negative infinity to 2 and from 2 to infinity. However, what happens here, and I'm not going to probably be able to draw this worth a darn here, but we have a hole in the graph, like this, at x equal 2. So whereas this is non-removable, this would be removable discontinuity. Now that's not what it's asking about. It may ask you a question about that later. Find where it's discontinuous and describe if it's removable or non-removable. But in this case, because it's just a hole in the graph, we would say that this is removable discontinuity. Let's try another one. All right. H of x is equal to, now this is a multi-rule function, it's equal to x plus 2 for x less than or equal to 0. It's equal to x squared plus 2 for x greater than 0. Now both of these are polynomials. And polynomials, y equals x plus 2, y equals x squared plus 2, those are continuous functions. They're everywhere continuous because we know a little bit about the graphs of polynomials. This one's going to be a line, this one's going to be a parabola. There's not going to be any holes or vertical asymptotes or any kind of gap. But because this is multi-ruled, we have to be careful. We know it's going to be continuous for x less than 0. We know it's going to be continuous for x greater than 0. But what happens at x equals 0? So it would help if you have a sketch to kind of see what's going on. So I'm not going to do a great job with this, but I'll give it a shot. So if I try to create a sketch here, I'm going to have, first off, this part is I'm going to have part of a line for those values of x less than or equal to 0. At 0, I'm at 2. So it looks something like this. It looks like a ray. And for this value here, let me grab a colored pencil. I always put them in the drawer, and then I forget to get them out in time for when I'm doing this kind of a video. This is going to be here An open circle at 0, 2, because if you were to plug 0 in, you would get 2, but it's not defined at, the second rule is not defined at 0, x equals 0, but it's a parabola, and it's going to go something like this. So you can see, because the ends connect, you can get a function, you have a function here that is continuous for all values of x, so it's everywhere continuous. I'm going to write negative infinity to infinity. No points of discontinuity. And this guy, this should be one of your favorites when it comes to continuity, because you know what this guy looks like, right? He just keeps going back and forth and back, and there's no holes, there's no gaps. This thing is also continuous for all values of x, everywhere continuous, negative infinity to infinity. All right, now to consider continuity on a closed interval, and this is a little trickier because we've defined it on an open interval. We didn't have to include the endpoints, because to include the endpoints, by the definition of continuity at a point, we have to use the limit as x approaches that value, whether it's a or b of your closed interval. Now, what we have to do here is to be able to consider continuity at a closed interval. We have to think of what we call the one-sided limits. Okay, so f is continuous on the closed interval from a to b, closed interval from a to b, if f is continuous at every point in the interior. And look at the notation here. The limit as x goes to a from the positive, or from the right side of f of x equals f of a, and the limit as x approaches b from the left side of f of x equals f of b. So we have an interval. Here's a, here's b. We have continuity in the interior, but on the left end point and on the right end point, we have to consider the limit. But because we're only looking at those values between a and b, we have to look at it from the right side here at a and from the left side here at b. Thus the notation. And we evaluate those limits the same way, except that when we're considering it, we're only plugging in values that are either a little bit bigger than a or a little bit smaller than b. All right, so now let's consider these one-sided limits. As x approaches 2 from the left of the square root of 4 minus x squared. Okay? As x approaches 2 from the left of the square root of 4 minus x squared. As x approaches 2 from the left, that would be like 1.9, a little bit smaller than 2, 1.99, 1.999999. Well, if I plug those values in, 1.9, 1.99, 1.99999, and I square them, it's going to be a little bit smaller than 4. Just a little bit. 4 minus a little bit smaller than 4 is positive, but really close to 0, and the square root would be 0. So we evaluate the limit in kind of the same way. It's almost direct substitution, but we have to consider the left side, especially with a radical. Now in this case, the limit is equal to 0. We look at it from the left side. Numbers smaller than 2. Here's 2 on the number line. Numbers smaller than 2. 1.9, 1.99, 1.99999. Getting really, really, really close to 2. Over here, the limit as x approaches 1 from the right side, this would be a little bit bigger than 1, of the square root of x minus 1. So again, we have the square root. We can't take the square root of a negative and have a real value. So we have to make sure that the numbers that we're looking at here are going to be positive. And that's exactly what happens. A little bit bigger than 1. From the right, here's 1 on the number line, would be like 1.1, 1.01, 1.000001. It's getting closer and closer to 1. Well, closer and closer to 1, but bigger than 1 minus 1 is positive, but very close to 0, and the square root of 0 is 0. So we can evaluate those limits. Now here, it gets to be exciting, because this is your greatest integer function. And you had the greatest integer function in Algebra 2, and you had the greatest integer function in pre-calculus, or you should have. So I'm just going to give a quick refresher here. I know we've done a little bit of this earlier in the book, especially in, I think, the prerequisite chapter here. But our graph looks something like this, and it helps to picture the graph in this case. This is a great function to look at when you're talking about continuity, because you've got all these breaks. Remember that the greatest integer of x is the largest number less than or equal to that value of x, the greatest integer less than or equal to that value of x. So we get this step function, and you can see why it's called a step function. At least I hope you can. Now as x approaches 2, well, from the left side, as x approaches 2, I get 1. because all these values are up here right at 1. But as x approaches 2 from the right side, because this is a two-sided limit, from the right side, I get 2. Because now it's up here, these values are up here. So the limit from the left side and the limit from the right side, not the same. So we can say in this case that it does not exist because the limit has to be unique. And we can emphasize that with this very important following theorem about the existence of a limit. A function f, let f be a function and let c and l be real numbers. The limit of f of x as x approaches c is equal to l if and only if the limit from the left side as x approaches c from the left of f of x is l, and the limit from the right side as x approaches c from the right of f of x equals l. So the limit from the left has to equal the limit from the right. If it doesn't, the two-sided limit does not exist. And that's what happened here in this example. Now let's get back to that closed interval. All right, continuity on the closed interval. A function f is continuous on the closed interval from a to b if it's continuous on the open interval a, b. Now I'm kind of restating this, but a little bit more formally. And the limit as x approaches a from the right of f of x is equal to f of a, and the limit as x approaches b from the left of f of x is f of b. All right, the function f is continuous from the right at a and continuous from the left at b. When we have a closed interval, that's how we can discuss that. And then, speaking of discussion, it says discuss the continuity of f of x is equal to the square root of 9 minus x squared. Now, I don't know if you know what this looks like graphically, and it really is convenient to kind of picture what's going on. You don't have to necessarily graph it out, but if you can get a rough idea, well, relatively rough idea of what it looks like in your head, this is going to look like this as a graph. It's going to be a semicircle. It's going to be a semicircle that has center 0, 0, and not very good job there, and radius 3. So I can see in here that it's continuous everywhere inside. Now, inside between -3 and 3. I just have to be kind of careful in stating this because it says to discuss the continuity. All right, so this is continuous at on the interval from -3, the open interval from -3 to 3. But we have to consider what happens here on the left and on the right endpoints. So I'm going to also look at the limit as x approaches -3 from the right side of my function f of x. And I'm also going to discuss the limit here as x approaches +3 from the left side of the square root of 9 minus x squared. Do I get the values of 0 that I think I'm going to? Well, as x approaches -3, this has got to equal the square root of 9 minus the quantity -3 squared. As x approaches -3 from the right side, that would be like -2.9, -2.99, -2.99999. And I square that, it's a little bit smaller than 9, and 9 minus a little bit smaller than 9 is close to 0 at positive, and that makes sense. You can take the square root of a positive. So this is going to equal 0, and this is good because this is equal to f of -3. And in this case, if I plug 3 in from looking at values from the left side, as I approach 3, from the left side, I have the square root of 9 minus x squared. As x approaches 3 from the left, 2.9, 2.99, 2.999999, and I put that in and I square it. It's a little bit smaller than 9, and 9 minus a little bit smaller than 9 is very close to 0 but positive, and again I get 0, which is f of 3. So therefore, f is continuous on the closed interval from -3 to 3. It's continuous from the right at -3, it's continuous from the left at +3. Now, when you have continuous functions, you have properties that go along with it, so we need to state them. We don't necessarily always pick these out, but we do know that when we have continuous functions and we're doing some algebra with the maybe we're adding, subtracting, multiplying, and such of these functions, we're going to get continuous functions. Property of continuity. If b is a real number, f and g are continuous at x equals c, then the following functions are also continuous at x equals c. The scalar multiple, you take any scalar, b, times your function f, the sum and the difference, or the difference here, f plus g, f minus g. So if you add two continuous functions, you get a continuous function. If you subtract two continuous functions, you get a continuous function. If you multiply two continuous functions, you get a continuous function. And if you divide, you also get a continuous function, except that those values where g of c is equal to 0. So you have to make sure that the statement that g of c cannot equal 0. Now this gives us all sorts of possibilities here as far as our functions that are continuous. Polynomials with the sums and the differences and the scalars and the products. Rational with the division. And as it turns out, radical, because radical typically just means that we're raising it to a rational exponent. And then also, as it turns out, the trigonometric functions, including like tangent and cotangent, and secant and cosecant, because of the idea of the quotient. Now you have to be careful, because we know that with those functions, not with sine or cosine, but with the other four trig functions, that there are vertical asymptotes on the graph, and then we would not be continuous for all real numbers, but for the domain. Theorem. Continuity of a composite function. If all we ever had was the square root of x, or 1 over x, or sine of x, it'd be great. And to a certain point, it'd be boring, but it'd be great as far as this is concerned. This theorem allows us to indicate that we do have continuity of a composite function when you take a function of a function. Now you have to be a little careful with this. Let me raise this up a little bit. If g is continuous at c and f is continuous at g of c, then the composite function given by f circle g of x is equal to f of g of x is continuous at x equals c. So you see what has to be done here. The limit as x approaches c of this has to be f of g of c. It has to be the direct substitution. That would mean that it's defined, that the limit exists, and that the limit is equal to that value. When I taught this, you can see this is a very long section. When I taught this section in a more traditional classroom, just give me time to take a sip of coffee while I'm relaying the story. I could never get this entire lesson done in one class period. And I would usually have to spread it out over two, which I always thought was ironic, because I would have to break apart the lesson on continuity. And of course, continuity means there's no breaks. Well, with that joke already wasted, let's go on to this next one. Discuss the continuity of the following functions. Now, the cotangent of x, remember, is the cosine of x over the sine of x. So what this means is that the sine of x cannot equal 0. And that happens at plus or minus. Actually, we don't even have to write plus or minus here. We can just write pi k, where k is an element of the integers. Because at those values, sine is 0, and that means I'm going to have a vertical asymptote. So to discuss the continuity, watch how I'm going to write this. This is continuous from pi k, notice the parenthesis, pi times k plus 1, k being an element of the integer. So that, for example, if k is 0, this is between 0 and pi. If k is 1, this is between pi and 2 pi. If k is 2, this is between 2 pi and 3 pi, as well as with the negatives. So that would be one way to describe its continuity. Now, maybe the easier way out would be to just discuss where it's not continuous. You could say something like x cannot equal this. But since it says not discuss the discontinuity, it says discuss the continuity, I'd rather list it out this way. All right. Next guy up. G of x is equal to the sine of 1 over x when x is not equal to 0. Let me get my graph here ready. Oh, smokes. I should have done this ahead of time. All right, I think that's my guy. Okay, there's my guy, and there's my graph. Well, it goes nuts there for a second, doesn't it? And then it kind of slows back down. Well, what's going on here is this is an oscillating effect, and so we are not going to be able to get a set value. Even though it's defined at 0 here, we're going to have discontinuity at 0. It's because this thing never just becomes 0. It just keeps bouncing back and forth, back and forth, back and forth, back and forth. And so in this case, well, as it turns out here, as x gets really close to 0, what happens is this is getting really, really big. whether it's absolute value-wise big, and then you times your x here. So these are probably going to end up showing you what happens for really large values and really small values. The oscillating effect. Whoop, pointing to the wrong one. The oscillating effect. So this is continuous from negative infinity to 0 and from 0 to infinity. Definitely non-removable discontinuity at x equals 0. Now in this case, let me change my graph again. Let me just sneak in my x here. Okay, I'll see that. So what happens here when I graph this one, you can see it kind of bounces back and forth, but do you see how it's not going up as high and it's down as low? And that's because of this x here. This x is getting closer and closer to 0, which is making this value smaller and smaller. Remember, this is going to be between -1 and 1 inclusive. So times numbers that are approaching 0 are making this even closer to 0. And here it's defined at 0. This part isn't, but it's defined at 0 to be 0. So in this case, this is everywhere continuous. From negative infinity to infinity. This is probably a little deeper than you thought continuity was going to be about, but that's pretty much it. Now, the key to continuity is when we have functions that are continuous, there are certain kinds of things that we can determine from these functions that we can't determine if a function is not continuous at a particular value over a particular interval. So probably the most important thing that I'm going to mention, at least in chapter 1 about continuity, is the intermediate value theorem. The intermediate value theorem is definitely on your AP test. It shows up all the time, and it's kind of a cool thing in that it kind of explains completeness, if that makes sense. If f is continuous on a closed interval from a to b, and k is a number between f of a and f of b. Okay, so time to draw a graph here. Arbitrary here, just putting most of this in the first quadrant just for convenience. So it's continuous on the closed interval from a to b. So maybe it goes something like this. So this is f of a, and up here this is f of b. Hopefully you can see that okay. All right, now what this is saying is if we have continuity on the closed interval from a to b, and we pick some number k in between, let's say k is right here. It's in between f of a and f of b. Then it says there's at least one number c in this interval from a to b such that f of c is equal to k. Well, what that means is there's got to be a value here. There can't be a hole. There can't be a gap. There can't be a number that's missed. Every value will be in there, and it could be more than one. I mean, your graph could go like this. And then it would have one here, it would have one here, it would have one here. So this is guaranteeing you at least the one. Now, it doesn't tell you what it is. You know, that's what existence theorems do. They say, hey, it's going to be there. It definitely is going to exist, but it doesn't necessarily tell you how to find it. You might have to do a little algebra to find it. So this is clearly an existence theorem, and it's based on the property of completeness, which means there's no holes or gaps on the real number line. And it's very useful to find zeros of a function. I always like to tell students that when I was a freshman in high school, my first day in high school, I was about the shortest kid in the class. I was 5 foot tall. And by the time I graduated high school, I was 6 foot tall. So somewhere between my freshman year first day and graduation day my senior year, I had to have been 5'6". Even if it was just for an instant, I had to be 5'6", because my growth was continuous. It might have been slow at times, it might have been fast at times, but there was no gaps, there was no jumps. It wasn't like all of a sudden, an instant, I went from 5'5" and 7/8 to 5'6" and 1/8. I hit 5'6" somewhere along the line, my junior year as a matter of fact. So anyway, that means I have to hit every value in there. Whether it's from 5 foot tall to 6 foot tall. I had to hit every value somewhere in between. All right, now, to find a zero of a function, think about it. Let's go back to my graph. Grab a green pen. If my function, instead of being up here in the first quadrant, if I have f of a down here in the fourth quadrant, but I have f of b up here in the first quadrant. And remember, f is still continuous. So I don't know, maybe it does that. Do you see how it would be guaranteed the existence of a 0 because a 0 is a number in between a negative and a positive? So that allows me to use this theorem to approximate the 0 of a function that maybe would be very difficult to solve for. Because we know how to find the 0 of a function usually. What we do is we just set x squared, in this case for the function f of x equals x to the third, excuse me, I said x squared, x to the third minus 2x minus 3, determine if there's a 0 in the interval from 1 to 2. Well, and I'm going to explain what this means. Yeah, there's going to be a 0 because of the intermediate value theorem. See, if I substitute 1 in, f of 1 is 1 to the third minus 2 times 1 minus 3. This is negative 4. If I plug 2 in, this is 2 to the third minus 2 times 2 minus 3. So this is 8 minus 7. This is 1. So it's negative here at the left end point. It's positive here at the right end point. So that means somewhere in between 1 and 2, there has to be a value that gives me exactly 0. Now, I don't know what that value is. Again, remember the intermediate value theorem is an existence theorem. It doesn't help us to find it. That's where the algebra would come into play. But before graphing calculators came along, because of course the graphing calculator speeds this up a lot, we could use calculators and a method called the bisection method to approximate a 0. See, I know that in between 1 and 2, there's got to be a 0. So I go halfway. I bisect that interval from 1 to 2. Right? I take the midpoint, 1.5. I plug in 1.5. So this would be 1.5 to the third power minus 2 times 1.5 minus 3. So let me grab Mr. Calculator here. And 1.5 to the third power minus 2 times 1.5 is 3 minus 3. It's a negative number, negative 2.625. Negative 2.625, negative 2.625. Well, that tells me now that since at 2 it's positive, at 1.5 it's negative, it's got to be between 2 and 1.5. So we use the bisection method again. We take the midpoint between 1.5 and 2, which would be 1.75. And then I find f of 1.75. And I can continue doing this as many times as necessary to get it as exact as I want. And like I mentioned before, the graphing calculators, this was the way we did it. This is the way that we approached it. So we could keep on doing this. If I'm not mistaken, I think this is negative as well. I guess I could go ahead and do one more. 1.75 raised to the third power minus 3.5 minus 3 equals, I get negative 1.140625. Well, here it's positive, here it's negative. It's got to be between 2 and 1.75. So now, between 1.75 and 2, I take the midpoint, which would be 1.875, and I keep on going. If you've ever watched, what is it? The Price is Right. There's a guessing game where they have to guess the price of a car, or I don't know, a sailboat, something along those lines. And so what they'll end up doing is they'll go 1,000, 2,000, 3,000. And as soon as they find out that one is under and the other is over, then they'll go halfway. So if it's between 1,000 and 2,000, then they'll go 1,500. And then typically they don't keep going exactly half because the average American has trouble finding halves of numbers. They'll go 1,500, 1,600, 1,700, 1,800, and they'll get between 1,700 and 1,800, 1,750, whatever it might be. They'll work their way through till they can get an exact value. Well, it's kind of the bisection method in its purest form, I guess. So now, give these problems on continuity a good effort, and be sure to work on some of the practice problems before working on the assignment itself. Continuity is very important in calculus, and it's clearly going to be represented on the AP test as well.